So as you heard, my name is David Smith, and I'm pressing, there we go. And Jared gave me a great introduction, so you've probably heard everything you need to know about me. So with that, I'm going to jump right into the talk. And so as you might have guessed from the intro music, this talk was inspired by an episode of Silicon Valley. I don't know if anybody saw this episode from season 4, where Jin Yang builds an app on his phone that he could point at food, and it will tell you what the food was, except that it only worked for hot dogs. Funny thing about this episode only aired last year, in May last year, and at that time, the whole concept that you could have, and by the way, the time is not going down here, guys. The whole concept that you could have an app that you could point at anything and it would tell you what was in the picture was complete fantasy. Nonetheless, the producers did build exactly this app. They used TensorFlow and uploaded it to Core ML and ran it on a device. Actually, I think it was an Android device now that I think about it. They have a really good blog post that explains the process they used to actually build this model from scratch and train it, and it was quite pioneering. And today, this kind of stuff is pretty routine. And in fact, what I'm going to show you in this talk today is how you can build exactly an app like this. An app that you take a picture, you point it at something that may or may not be a hot dog, and it'll tell you if it is or is not a hot dog. And the way I'm going to do that is by starting with getting some images of hot dogs that I'm going to train a model with. And I'm going to get those images from a place called ImageNet, and I'll show you how to do that in a little while. Then we're going to train a recognizer using a process called transfer learning. And the really nice thing about this is you don't need to do that from scratch. I'm actually going to use an online service in the Azure cloud to do that and drive all that computation using R. But the end result of this is we're going to get a Shiny app that we can use. We can give it a picture or a URL of a picture. It will analyze that picture and tell us whether or not it's a hot dog. So let's see how to build one of those. Before I do that, though, I want to do a little bit of explanation about computer vision. And I'm going to gloss over many, many, many details during this very brief explanation. But if you do want to go into the details of how this works, and particularly the mathematics behind how computer vision works, I really recommend Brandon Rohrer's blog. He explains it in really clear and easy to understand ways, so check that out. And in particular, I borrowed this particular image from Brandon's blog. But let's have a look at how computer vision works. The basic idea behind computer vision is we have a neural network, which is basically a big bunch of matrix operations. We start off with an image. Here's a picture of my bicycle. And that image, all of the pixels in that image, goes to this node right here. And what happens at that node is a filter is applied. A filter in exactly the same sense as a filter in Instagram or Snapchat. That filter is defined by a small number of weights that get applied to pixels, typically 9 weights or 4 weights. But it's just a simple mathematical operation which transforms that picture, changes it somehow, and makes it a little bit smaller in the process. Same thing here. We do the same kind of process with a different filter here, different filter here, different filter here. We get 4 new images. We combine the 4 images together and do a new filter, which makes the image smaller again. A new filter, a new filter, a new filter, another layer in the neural network. Same process happens again. So as we apply all these filters rather, and combine the pictures together, we're inferring more and more information somehow about that picture. This particular neural network is a very small one by computer vision standards. It only has 4 hidden layers, but it's also only designed to detect 4 different classes of objects. It's designed to detect dogs, bicycles, apples, and tennis balls. And you can see that as we take this picture of a bicycle and process it from filter to filter to filter, the image gets smaller and smaller and smaller until at the very last layer, we combine everything together and that entire picture has converted to one number, which has been between 0 and 1, which you can think of as the probability or the confidence that the picture represents one of these 4 classes. And you can see that in this particular case, it's working well for this bicycle because that's the one that gets the highest score, and this neural network would classify this picture as a bicycle. Well, how do we get to this stage? Well, we train it with thousands and thousands, possibly even millions of images. And we choose the weights of all of those filters such that pictures of bicycles get the highest score here, pictures of dogs get the highest score here, and so on and so forth. How does that work? It doesn't matter. It's really just an optimization problem. It's just log likelihood, if you like it. It's not log likelihood, but it's very, very similar. There are great tools out there that do this optimization process. You don't care anything about backpropagation or ReLU or anything like that. Just know that these weights are optimized such that this condition holds true. So that's the way basic computer vision works. What if we want to classify pictures that are not one of those classifications that the trained neural network is designed to recognize? In our case, what if we want to recognize something other than dogs, apples, tennis balls, or bicycles? What if we want to identify hot dogs instead? Now, of course, we could go back to the drawing board, get millions of pictures of hot dogs, train one of those neural networks in the same way, but that takes a lot of time, takes a lot of money, takes a lot of computation. But there is a shortcut that lets us do just as well with much less data and much less time, and that's called transfer learning. We could take that same network that we just trained already to detect dogs and bicycles and so forth, strip out the last layer that does the classification, and instead take a new image, run it through that pre-trained neural network, and then just grab the numbers that exist in that second to last layer. We don't know what those numbers really represent, but that we call them features. We get 8 numbers for every image: F1, F2, F3, F4, F5, F6, F7, and F8. And then what we can do is take some pictures that represent the classification that we want to detect with transfer learning. Let's take hot dogs. Let's start with something that's not a hot dog. It's a picture of a burrito. We can run it through that network. It's going to give us 8 numbers and a binary classification, 0 or 1. Let's do it again for a picture of a hot dog this time. Run it through that same network. We get 8 numbers and a binary classification. And we can do that again and again and again for a couple of hundred pictures. So we get a couple of hundred sets of 8 numbers, a couple of hundred binary classifications. What does that sound like to you? That's just logistic regression, right? We could build a pretty simple model which, given this data, predicts this classification, and it turns out it works pretty well. We don't really know why, except in the sense that this whole process of applying filters, when you get down to this last layer, you can imagine each of these data points here as representing something intrinsic about the image generally. We don't really know what, as I said, but this one might represent the greenness of an image. This one might represent the number of circles in the image. This one might represent, if it was working with faces, the number of eyes that it detects, those kinds of things. It's pretty difficult to figure out what they represent, but when you apply new images to them and do this reclassification process, it turns out it works pretty well, especially when you use a network that's trained on images that are somewhat like what you're working with. So in my case, I'm actually going to work with a network that was trained on food items, and it turns out well that it detects features of food pictures really well. That makes this classification works really well. All right. And you don't even have to code this up yourself. There's a nice service that is available in Microsoft Azure called Microsoft Cognitive Services Custom Vision, which let you just take a bunch of images that represent the classes that you want to detect. So in my case, I'm going to give it a bunch of images of hot dogs and a bunch of images of things that look kind of like hot dogs that are not, so it can discriminate a bit better. I can just upload them to this service, and it will build one of these transfer learning models for me. Has a nice sort of web UI. Here's an example for this particular project that I'm working on here, where I've got 61 pictures of hot dogs, 78 pictures of things that look like hot dogs but are not. And you can do all this kind of stuff through the GUI, but that didn't work for me in this particular case, because although you can just upload a bunch of pictures from a folder into that service, I don't have pictures in this case, because I went to ImageNet to get pictures of hot dogs. If you're looking for a source of general images by classification, ImageNet.org is a really useful service. It's a website that's been going for about 10 years to drive competitions in image analysis, which is actually what generated these pre-trained models that we're using today. You can, for example, search for hot dog, but what you get out of that if you download things is just a list of URLs that represent the hot dogs on the web. And so it would have been a real pain for me to go to each of these and download them and then upload them into the service. So instead I used R and interfaced with the API for Custom Vision to do this. So to get my images to work with, I searched for hot dogs on image.net and also things that were related like frankfurter buns. That gave me about 2,300 URLs to work with. Similarly, for my contrast set, things that look like hot dogs but are not actually hot dogs, I looked for tacos and hamburgers and got about 2,600 images for that, but I don't need that many. It turns out you only need a couple of hundred images for transfer learning to work well in a pre-trained network that's related to your field. So I just sampled 100 from each of those lists using R. All of the code for this, by the way, I will give you in a GitHub repository at the end of the talk. And then I just wrote a function in R to upload them to the Custom Vision service. The only thing you need to make this work is a key to access the service, and you can get that for free from Azure, details in the blog post. But here's the function I use, upload URLs. I give it my vector of URLs and the tag I'm using, and it uploads them into the system, and you get what you saw in the previous slide. There is a bit of a problem with this, however, working with data with ImageNet at least. And that is when you search for hot dogs, you get things like this. As I said, that site's been going for about 10 years. Many of the images are on Flickr. And when images are deleted from Flickr, it's not kind enough to give you a 404. It just gives you a black screen like this. No, it gives you this, this little icon, which is an image, but it's not an image of a hot dog. So we need to figure out how to deal with that. I've lost my monitor. Oh, there's my monitor as well. Okay. Here is another image of a hot dog that you get by searching for hot dogs in ImageNet. It's a woman who is eating something that is not a hot dog, but is apparently an ice cream sandwich. So we wouldn't want to have that in our image sets for training. And here's another example. It's adorable. It's gone. It was adorable, but it's not a hot dog. So there is a decent amount of data cleaning that you would need to do to make this work. And of course, you could have a look at those URLs individually and just remove them from your vector in R before you upload. But actually, this is one of the things that the web interface is really convenient for. You can actually browse through the images, select ones that you want to retag or delete. And in this case, it's my little dog. And we'll get rid of the dog by pressing delete. So that was how I could have filtered out or cleaned up my data before my transfer learning training. And after that process is complete, you can see we've got 61 images of hot dogs. They're in all sorts of categories, if you guess. Sometimes there's multiple hot dogs. Sometimes there's other things in the image, like a person or other bits of food. Sometimes it's a bit blurry, but this is the kind of data that we're using to do training. As we'll see, it works pretty good. And then for things that might be mistaken for hot dogs, tacos, hamburgers, and so forth, I've got those in there under another tag to do the training. So now, when we want to do the training, we've got our images uploaded into Custom Vision. We tag them as hot dog and not hot dog. When you do the training, you have to choose something called a domain, which is the pre-trained network that's used to do the transfer learning when they strip off the last set of categories. There are domains that have been trained with just all sorts of images, and that's generic. There's one that's been trained with landmarks. There's one that's been retrained with photos that you might see in an online shopping catalog for retail applications. There's one that's been trained with adult images, which is mainly used for content filtering when people upload bad stuff. The one I use is the one that's been trained on food items, which is why this works so well with so few images. You can just click a button in the in the website rather, to launch the training process. But I wanted to kick it off from R so I could automate this. And this is just an example of how we're interfacing with the API directly. There is a very nice API that's all documented online. And with the HTTR library, which is lovely, I can just interface directly with the endpoint that kicks off training, and then just check it for a few times until it's completed, because the training takes about 30 seconds and happens asynchronously. But once that is done, I have a trained model that I can pump an image into. Before that, it's worthwhile having a look at how well your model is doing, and you can have a look on the website to do this. It shows you these machine learning terms, precision and recall, which I can never remember what they mean. I just remember that this one is the false positives. Of all the images in our database, how many were incorrectly classified, and this is the impact of false negatives. Of the things that weren't the thing, when did it classify it as the other thing. And of course, this is all dependent on our probability threshold. Remember that number that came up at the very end that was between 0 and 1? We can choose how high that number has to be before we classify it as either that thing or that other thing. And so how you choose that number depends on how the false positives, how many false positive and how many false negatives you get. Think about that carefully. It doesn't matter too much when I'm trying to classify hot dogs, but if you're trying to classify, say, cancer from an image X-ray, the impact of a false positive is a lot worse than the impact of a false negative. So how you choose that number is really, really important depending on the application. All right, next slide. Once we have trained the model, I've written a function in R called Hotdog predict. I can just pass it in a URL and that threshold that determines the classification. And the same kind of thing again, just get to the endpoint, pass in the image URL, and get the response as JSON from the API. And then using the JSON package, I can just extract out the predictions for that particular classification. So I could do that from the R command line really easily. So here is the URL of some hot dogs on the grill, and it comes back that the hot dog classification is 99%. The not hot dog classification is less than 1%. So just about any threshold, this would classify it as a hot dog and not as a not hot dog. Another example. Here is the burritos. Here is my URL of pictures of burrito with rice from Wikimedia. Also a great source, by the way, of images, searching in Wikimedia. And this one is classifying it as a hot dog at 10% and a not hot dog at about 80%. So with a threshold somewhere in the 50-70% range, it would make that classification correctly. But it's not so much fun to do it just from the R command line. Let's actually build an app to do this. There are several ways you can encompass these predictions into an application. You can do it offline. So if you wanted to run it sort of on a server that wasn't connected to the internet, or probably more realistically on a phone application, you can export it as Core ML, so to run on an iPhone. You can export it as TensorFlow, so to run on Android. You can also export it as Onyx, which will run in lots of different platforms. This is a general open source framework for defining trained predictive models with deep learning. Or you can export it to a container, which will run on anything like a Raspberry Pi, for example. The nice thing about that, it's fast. You don't need any internet connection to make it work, but you are limited in the size of the underlying neural network that you use just for performance reason on these small devices. And so there's something called the compact model in custom vision, which is a very small general model, but works pretty well for these offline applications. Or you can do it online. If you're connected to the internet, you can connect through the REST API, and you saw me doing that from R a minute ago. And I'm going to use those same functions to connect to a Shiny app just through the endpoint that the service provides me. The code for the Shiny app is available on GitHub, but let me just show you how it works. First of all, let's start with an image that is not one of those classifications. This is my dog Easy. Here's the URL of the picture of him from the blog, and you can see that even at the 50% threshold, he's very confidently classified as not hot dog. He is a hot dog, but he's not a hot dog. All right. Here's another example. So this is a hot dog. I come from Chicago. This would never be classified as a hot dog in Chicago. Nonetheless, my app does indeed classify it as a hot dog. So it's interpreting this particular thing as a hot dog. Another example, these are some spring rolls. And you can see my app is classifying that as a hot dog. This is a good example of a misclassification here. It is dependent on the threshold. I've got a slider over here which you can manipulate in the Shiny app. If I bump that threshold up to next slide, please. There we go. You move this slider up and down, and you can see that the threshold for that particular picture was 52%. But this is a good example. Like if you're finding things are misclassified that shouldn't be, this is a good prompt to you to put some more images into the training set and retrain so I can better discriminate these types of things. So I would add some pictures of spring rolls to my training set, and hopefully this kind of thing would be fixed. All right. It was really nice building this. Next slide, please. It was really nice building this as a Shiny app. Really easy to do as well. And one of the really nice features of Shiny is setting reactive inputs. And if you haven't played around with it, sort of the long story short is that when I call out to the API, it caches the values that it has previously requested, so that as I move that slider back and forth, it's not going back to the API anytime. It just uses the categorization from the API and changes the output in the Shiny app. That's really nice because it saves me money, because it doesn't have to make a query back to the API every time. Although actually in this case it doesn't matter, because I'm using the free tier of custom vision, which is completely free, up to 2 classifications per second, which is enough for an API, for a Shiny app. But if you have a sort of production application, you can do it for 10 cents, or 1 cent for every 10 classifications. All right, so that's it. If you want to find, oops, next slide, please. Just to summarize, it's really easy to do these transfer learning classifications using the custom vision.ai app. I was really surprised at how few images you need. Like I said, I just needed less than 200 to build that app. It's really fast. It just takes seconds, actually, rather than days you would require to build up a complete custom computer vision network from scratch. And you can do it either offline or as a REST API, and you can drive it from R with the HTTR package. And so, on the next slide, you'll be able to find the GitHub repository where you can get all the code for the classification and the app. If you want to try it, go to customvision.ai. You do need an Azure account, even though it's free. You can get a free account at this link here, which will also give you 200 credits if you're $200 in credit if you're a new user to do anything you want on Azure. Thank you.